Now we're going to look at the energy of an electron when it totally leaves the atom, not just going up to a higher energy level, but totally leaving. And so that would be kind of like it going to n equals infinity up to a higher and higher number until it has totally left. So let's consider what happens to our equation. As n approaches infinity, then the energy would approach, the denominator getting larger and larger, it would approach zero. So that's how we say the energy of the electron is zero for an electron that has left. That makes sense because there's no potential energy that's relative or relevant to the attraction between the nucleus and the electron if the electron has totally left. Okay, so what if an electron goes from its ground state in hydrogen to n equals infinity, it's totally left. So when we do think about this, this is going to be our initial, and this is going to be our final. And so the change in energy for the electron, or in this case for the atom, is going to be the final minus the initial. And I will leave it up to you, this is on your lab report, I will leave it up to you to calculate that number. But this number will come out in joules, and it is for one electron, but we are calculating it for the atoms overall. How much energy. So this will be in joules per atom. Okay, and so I'll let you come up with that number, and then next you're going to need to convert it to a mole of hydrogen atoms. And so what you're going to do, you're going to take your joule per one atom, whatever number you have there. You know, when we think about numbers of atoms and going to moles, what do you think we use there? For that step, you'll need to use Avogadro's number. And then also we're going to convert this to kilojoules. The figure can be found in any chemistry book or online or whatever, showing the different line series. I wanted to point out that first, my energy levels may not be exactly to scale, but there is a bigger energy difference between the lower energy levels than as you go up higher. They go closer and closer. And that means that if an electron drops all the way to the first, it will necessarily have more energy than any of the drops to the second and to the third, and so on. So all of the transitions that go to the first involve a lot of energy per photon, and they will end up being in the UV range. All of the transitions that end at n equals 2, the second energy level, will end up being kind of medium, and they will end up in the visible range. And notice there are 4 of those here, and our calculations will have those 4. And then, of course, we could say the same thing about the ones that drop to the third. So visible, this is our electromagnetic scale, part of it. Okay, so the ones that drop to the first have the most energy, and they're in the UV, and so these are higher energy. They're going to be higher frequency and shorter wavelength. Okay, and at the other extreme, these transitions that don't involve as much energy those photons will be lower energy, lower frequency, and longer wavelength. So you see we could make some statements that if you compare two transitions, if you compare a transition of n equals 3 to n equals 1 versus if you went from 6 to 2, all that matters, it doesn't matter how many energy levels are involved in the transition. This one involves more levels. What matters is where it ends because of this large gap here. So this will always end up in the UV, and this will end up in the visible, which is less energy.